If you've spent any time tracking large language models, the big paradox, right?
Hmm.
They can do these incredible things. But the second something goes wrong, trying to figure out why, it feels like staring into a black box. It's
Yeah.
totally opaque, it's frustrating, and honestly, it's a huge barrier to making AI truly safe.
It's the core challenge. I mean, that's why model interpretability has been such a bottleneck for so long. But that's what we're diving into today. The Google DeepMind release of Gemma Scope 2.
Biggest.
And you should really think of this as the essential microscope we've needed.
A microscope.
Yeah, it's a tool that could shift AI safety research from just, observing behavior to actually mapping the internal code these models are learning.
And the scale of this project alone just tells you how serious they are. This is the largest ever open source release of these kinds of tools from any AI lab.
Mm.
To put this in perspective for you, it involves storing around 110 petabytes of data. That's just a staggering amount.
Yeah.
And training tools on over 1 trillion total parameters. Okay, so let's unpack this. How does all of that computation turn into a way to actually understand what's going on inside?
Well, interpretability research, at its heart, is about revealing the learned algorithms inside the model. And Gemma Scope 2 gives us that visibility across the whole Gemma 3 family of models. So from the small 270 million parameter ones all the way up to the big 27 billion parameter ones.
So what's the mechanism? How are they actually peeking inside to see the quote-unquote thoughts?
It's a combination of two key things: sparse autoencoders, or SAEs, and something called transcoders.
Okay.
Think of the model's brain as this huge dark attic just full of concepts. The SAEs are like these very sensitive scanners that can go in and find one specific recognizable concept, like, say, the concept of causality, or even a refusal to answer a harmful request. The SAE gives that concept a unique address.
So if the SAEs find the concepts, what did the transcoders do?
The transcoders connect them. Models process information in layers, right? Like chapters in a book. A transcoder can see how an idea learned in, say, Chapter 3 is being used or changed in Chapter 8.
Got it. So you can actually trace a thought process.
Exactly. You can see how these concepts connect and lead to the final behavior you see on your screen.
And here's where it gets really interesting, because that full coverage at scale up to 27 billion parameters, that feels like a major breakthrough. Why is that size so important?
It's crucial because that's where we see emergent behaviors. These are capabilities or risks that just don't exist in smaller models. They sort of pop into existence at scale.
Like this story about a 27B size model helping discover a new potential cancer therapy pathway, right? That was an emerging capability.
Precisely. These tools are designed to understand that kind of emergence, whether it's something amazing and beneficial or something potentially very risky.
That's incredible. But I imagine analyzing that complexity requires some seriously advanced tools. What did they add to manage that scale?
Oh, yeah. They really engineered this for detail. The tools are trained on every single layer, not just a few. And they've introduced new things like skip transcoders and cross-layer transcoders. And
What do those do?
they're for deciphering really complex algorithms that jump across multiple parts of the model at once. They also use the Matryoshka training technique, which helps the SAEs detect concepts more accurately. It's all about mapping high-level algorithms.
So we take these incredibly technical tools and connect them back to the AI safety community's goals. What practical safety problems can these tools help with right now?
A lot of the effort went into specialized chatbot behavior analysis, specifically for the chat-tuned Gemma models. So they can now do these deep studies of things like jailbreaks, how prompts get around safety filters, and they can analyze the model's refusal mechanisms. And crucially, they can assess something called chain of thought faithfulness.
Okay, let's simplify that last one. What does chain of thought faithfulness really mean?
It means checking if the model is, well, basically lying to us about its own reasoning. It's the difference between the step-by-step logic the model shows you and what its internal state was actually doing to get the answer. These tools help see if that story matches reality.
So what does this all mean then? The mission seems clear. Give the global safety community the tools to finally audit these AI agents and debug their emergent behaviors. They've handed over the keys to the black box.
Precisely. And if you think about the bigger picture, given that these microscopes let us trace risks across the model's entire brain, think about what comes next. We might soon shift from just observing risks like sycophancy or hallucinations to maybe, just maybe, actively performing a kind of neuron surgery, going in and directly shaping the internal algorithms themselves. That's the real paradigm shift here.